everybody for the afternoon session. It's my pleasure to join this session. We have two talks. The first talk is by Frédéric Legoll on Multiscale Finite Element Methods for advection-diffusion and reaction-diffusion problems. Please, the stage is yours.
Thank you very much for the introduction. Thanks to the organizer for having me here and keeping the community alive. So it's nice to see people that are new, and it's nice to see new faces as well. I hope that this will pursue at least until 2026, we heard yesterday, and maybe other events as well. Okay, so I'm going to talk about multiscale finite element methods in the spirit of the method introduced by Yalkin this morning. And I'm going to deal with two different problems, advection-diffusion problem and reaction-diffusion problem. So this will be the two parts of the talks. I'm sorry for those who already heard the first part. Cannot reinvent everything every 3 months. But the second part is completely fresh. Okay, and this is joint work with Rutger, who is now in a nuclear French agency, Claude, Alberic Lefort, who is doing his PhD with us, and Alexei Lozinski. Okay, so we're interested in multi-scale problems, and it's not that useful to motivate this in front of this audience, whether they would be manufactured, made for aircraft, or, and Yalkin already gave examples this morning of underground reservoir modeling with a very heterogeneous structure. Okay? So let's dive into our first problem of interest, which is a advection-diffusion problem. So we have a diffusion component here with a highly oscillatory tensor A epsilon, and here is some typical microstructure, for instance. And on top of this, we add a convection term, B grad U. B will be divergence-free in all these talks, so from the theoretical point of view, there is no issue. And we are interested in the case of B being large. So there are two types of motivations for this problem. The first one is a mathematical motivation. We spent a lot of time in our team doing the diffusion equation, and so we wanted to go elsewhere and to go, for instance, to a non-self-adjoint problems. And this is why we are going to play with B, and B will be large in order to be far away from the purely diffusive regime. Okay? So there will be actually two scales. There will be the scale of the heterogeneities, A epsilon, and the scale created by the fact that B is large and there will be thin boundary layers, and I will come to this in a moment. Okay? The nice point about this equation also is that in homogenization theory, there are three usual suspects. There is the original oscillatory equation, there is the corrector equation, and there is the homogenized equation. And for the diffusion equation, all these three guys are purely diffusive equations. And now for advection-diffusion problems, the three equations may be of different nature depending on the scalings. Okay, so it makes the things a bit richer. From the application viewpoint, you may think of pollution in a city. Here is a picture of a city with buildings. So you may see that as a multi-scale problem in the sense that this is a perforated domain where the wind and the pollutant do not enter the buildings but just travel into the air. We have Navier-Stokes equation for the air, and this equation would model the diffusion of the pollutant into the thing, and B would be the velocity given by the Navier-Stokes equation. Okay? So this is a problem posed on a complicated domain, perforated domain omega epsilon, and we're going to replace this problem by that one, where omega is omega and the multiscale nature is embedded into the diffusion coefficient. Okay? All right. So let me explain in a few slides the basics of MsFEM, just as Barbara did for LOD and just as Yalkin also recalled this morning. So this equation here was the basis for multiscale, the multiscale community, and there are two big families of methods to address this problem: the Multiscale Finite Element Method, which dates to 1997 by Yalkin, Tom Howe, and Wu, and the local orthogonal decomposition method and its followers, already introduced 10 years ago now, it's a long time, by Axel and Daniel. And both methods share the fact that we are going to address the original problem with suitably chosen basis functions. Okay? So for the MsFEM, here is a cartoon of how it goes. We introduce a coarse mesh. This is this mesh with the big elements here. We don't care about the heterogeneities, which are symbolized here by these red dots of the size of epsilon. And on each of the coarse elements, we are going to solve a problem which mimics the problem that we are interested in. So here we keep the same operator, minus divergence A grad, with, say, a 0 right-hand side. And we need to invent boundary condition on the boundary of this coarse element. And the simplest boundary condition is just to impose a fine boundary condition. And we will discuss this later on in the talk. Okay, so this is the 101 method. It's not the best method, but it's just the mother of all the methods that will follow. Okay. And of course, this problem, we discretize it in practice on a small mesh of size little h, h being much smaller than the heterogeneities, but it's a local problem, so it's not that expensive. And all these problems are computed separately on each of the coarse element, and they do not depend on the right-hand side, okay? So you do that as an offline stage, and then in the online stage, you have them at your disposal. Here is a picture of a 1D setting where we have A epsilon varying differently on the left-hand side and the right-hand side, and the basis functions are not the same on the left-hand side and the right-hand side of the domain, and here capital H is 1 over 5. Okay, so there are 5 basis functions. All right. Okay, and now the online stage consists in doing say a Galerkin approximation, but you may also play with Petrov-Galerkin, that's been in the literature, of the original problem on these basis functions. All right, so advection-dominated problems have an additional difficulty if the advection field is very large. Okay, and this is well known, and it also appears in the single-scale framework. So I go back here to a simple Laplacian term for the diffusion. I keep my convection B grad U. I keep divergence B is 0, and it's well known that there is this Peclet number which measures the strength of the advection with respect to the diffusion. Okay, so H, the time of the size of the mesh, times B, the size of the advection field, divided by alpha, which is here, it's easy, it's just the diffusion coefficient, but then when we will turn to a multiscale framework, knowing what to put here and is more complicated because we will have a diffusion coefficient that varies between 2 values, and which one should we pick? Anyhow, in here, this is just a single scale framework, so this is a clear definition. And if Peclet is large meaning say 8 here, we have this kind of result. So the blue line here is the exact solution, with a B going in the right direction. And if you do P1, you will find this green solution, which is, of course, so this is the first size of the mesh. It's, of course, wrong in the boundary layer, because anyhow you are trying to approximate this exponential shape by a linear, so we have no hope. But the pity, and this is why it's not good, is that these oscillations propagate in the full domain and pollute everything. Okay? And okay, so it's an old problem, and it has been addressed by various ways, and the method I will play with here is stabilization by SUPG method. And the result is the red curve here, which is bad in the boundary layer, but which is extremely good outside the boundary layer. SUPG consists in adding some artificial diffusion, actually, to compensate for the fact that the continuous problem has a very small diffusion compared to the convection. So you add numerical diffusion to stabilize the stuff. And SUPG consists in doing this variational formulation where we add this green term, this stabilization term, which reads this way. The red part is the operator, L of U, UH, the numerical solution, and the black part here for SUPG is the skew symmetric part of the operator, which is B grad U, and there are other methods like Galerkin-Lewis square or other things where this black term would be different. Okay? And to keep the method consistent, we also add a term on the right-hand side, this red term being thought as the right-hand side f, and this that v is the same as t. Okay? And there is this tau coefficient here, which you have to choose, and there is a huge literature on how to choose the tau, and actually the numerical results are also kind of sensitive with respect to the tau. In the 1D setting, there is a clear picture, and people have a good formula for the tau that they buy for the 2D case, and it works, but as soon as we will go out of the single scale framework, it will be part of the question on how do we pick the tau. The tau should depend on alpha, and so which diffusion parameter should we pick, and so on and so forth. Okay. All right, so now we have the two building blocks. We have MsFEM to deal with the highly oscillatory diffusion, and we have stabilization ideas to deal with the strong convection. And what we want to do is to take the both ideas to address the convection diffusion problem in an oscillatory setting. Okay? Okay, so there has been many tries, either in the MsFEM context or in the LOD context, with in particular this paper which recently appeared. And I'm going to build on our previous work and go further. Okay. So we have an operator, A, which includes a diffusion term and a convection term. And so you may think of building the MsFEM basis functions either using only the diffusion term or using both components. And the B here, in my setting, the B is not oscillatory, and it is important for this red variant to be related. And that's up to you to either use only the higher order operator or the complete operator. Okay. This is here the P1 basis functions associated to that node here, and this would be the advection basis function, so the solution to this equation as the wind goes stronger. So Pickley is 1 here, Pickley is 10, Pickley is 50, and we see the basis functions which is pushed to the top right corner because the B here in these numerical experiments point towards the top right corner. Okay? And in all of these methods, we have one basis function associated to each node of the coarsemesh. Okay. Once you have built these basis functions, this is the offline procedure. You go to the online procedure, which is doing a standard Galerkin approximation, or either on this space or on that space. And of course, this A now includes both terms, okay? Diffusion and convection. Okay, so let's see how it goes. Here is a typical example of a advection field B, which is slowly varying. So the B is not constant, it's turning a bit. It is of norm 1, it is divergence free, and this is here the reference solution that we are trying to get, where you see on the top and on the right boundary, there are these boundary layers. Okay? And on the scale of the figure, it's not, I mean, the oscillations cannot be seen because anyway, I plot the solution, and the solution has small oscillation. I should plot the gradient to see really the oscillations of the function. Okay. All right. As I said, if you do a single scale problem, and if you do what's considered as a good method, which is P1 SUPG, you're not going to capture the solution in the boundary layer. Okay? So we are not going to be more courageous than in a single scale framework, okay? And we are going to ignore the error that we make in the boundary layer and just focus on the domain here, which we called outside the boundary layer, and we will declare that we are doing a good job if we already capture correctly the solution in that part of the domain. Okay, and in the last slide of the talk, I will go back to what happens in this boundary layer. Okay. So we just look at outside of the boundary layer in this blue zone. Okay, so here is the first plot. So all the plots will be relative errors in the H1 norm. With respect to alpha, alpha sits here and it measures the strength of the diffusion. So when you go to the left-hand side, alpha becomes smaller, meaning that the diffusion coefficient is smaller, and so it's more and more convection-dominated. Okay. This black line here is more or less Beckley's 1, so this is the separation between convection-dominated and diffusion-dominated. And this black line here is 100% of error, where this is complete nonsense. Okay. This is the MsFEM approach. So just you build the basis function with the diffusion operator, and this is it. Okay. So in the diffusion-dominated regime, it performs well, 10% of error. But as you put convection in, or as you decrease the diffusion, it goes to very bad result, and this is expected because if you think again on a single-scale problem, MsFEM is just P1, and we know that P1 performs badly when there is a lot of convection. Okay. Now, more surprisingly, if you build the basis functions including the field, the advection field, the results are not that better. Okay, and you do like 40% of error. So it's a bit better, but not that better. And again, if you consider a single-scale framework, you may interpret this method as a P1 method on a stabilized formulation, and you will see that the stabilization parameter that pops up from the computation, and you have no handle on it, it's just built in the method, is too small. Okay, and this is an old observation from the people from the residual free bubbles and all this community about single-scale advection diffusion problems. Okay, so they know this problem for the single-scale setting, and in the multiscale setting, we still have this issue. Okay, so it does not perform better. Okay, so let's start to do what people did in the single-scale framework, which is to stabilize. Okay, so we're going to stabilize by adding this stabilization term here and adding this additional term on the right-hand side, and we copy for the stabilization term in the bilinear form. We copy the way that people do in the single-scale framework, which is to take the operator here, L of u, so now that's the highly oscillatory operator, and here put again the skew-symmetric part of the operator, okay, and you have the F here. Okay, and for MsFEM, for instance, this term will vanish because the basis functions make this term vanishing, and for add MsFEM, the complete red term here would be 0, so the stabilization would be void for add MsFEM. If you do that, this is the result here. It works much better, okay, and you reach errors which are of the order of a few %, and it's a very nice thing, okay. And this is the point that we reached a few years ago, and we are happy with this method, except for the fact that you have to find a tau, okay, which is the stabilization parameter here. So for that simple academic 2D problem, we're able to design a good value, but it may very well be the case that on a more complex problem, it's much more difficult to find a good value of tau. Okay? So this is why we wanted to move on and to pursue the idea of this add MsFEM method, but to go further. Okay. All right. So we tried many different things, and 90% of the things that we tried failed. And I'm going to tell you about what succeeded, and it's not, there is a long story behind this, okay? What did work was to simultaneously add two ingredients into the method. The first thing is to add bubbles. And again, this is something which is kind of traditional in the advection-diffusion community to add bubbles. Okay, so that was not very innovative from our side. The other point was to change the boundary condition on the local element. Okay? The thing that we tried also is oversampling that most of the people may think about, because this is a classical idea for MsFEM, and it does not work. It does not work in that setting. Okay? So what did work was to change the boundary condition on the local element and to use Krauser-Raviart type boundary conditions. So let me explain this. We are going to solve now. I forget about the old construction of the MsFEM, and I go to this construction. I consider the operator, and I consider the full operator with the B here. And I'm going to, so it is equal to 0 again, as before, but I do not impose strong Dirichlet boundary condition on the edges of the coarse element. I'm going to impose weak boundary conditions. So what I do is I impose that the average of the basis function, phi, is equal to 1 on one of the edges of the triangle and 0 on the two other edges. Okay? And to make it well posed, I also impose that the flux here should be equal to a constant. Okay? So you may think of this as minimizing a quantity with this constraint, and that equation here is the Lagrange multiplier of the constraint. Okay? So the flux is a constant, and the constant pops up from the fact that you have prescribed the value of the phi, its average, to be 0 or 1 on the edges. Okay? If you do that without the B and with A epsilon being equal to 1, so you do that with a pure Laplacian thing, you go back with this construction to the standard Krauser-Raviart element, which are piecewise affine, and for which you control the average of value on the edges, meaning the value at the midpoint. Okay? So this is here the picture. Now we have basis functions which are associated to edges. So this one here is associated to that edge. Its average here is 1. Its average on all the other elements is 0. And this is how it goes. Okay? And a priori, there is no continuity along the edge. There will be no continuity along the edge. Okay? So this is the P1 basis functions. Now we insert A epsilon, we insert B. And this is how it goes. So there is a function epsilon and with the Peclet, and you see again the Peclet pushing the things toward the top right corner. Okay. This is the first ingredient. The second ingredient, and you need both. Actually, we tried either of the two, and it does not work. You need the both. The other ingredient is to use bubble. So we say that the operator should be equal to 1, and again with Krauser-Raviart or weak boundary condition. So these are bubbles that vanish only on average on the edges. Okay? This is this equation. It varies, it vanishes on average, and the flux again is equal to a constant. And this is this picture here of a bubble for some value of the Peclet number and some value of epsilon. Okay. All right. So now we have these two guys. Bubble functions and so we have basis functions associated to elements, these are the bubbles, and we have basis functions associated to the edge, which was the previous ones. Okay? And everybody is defined with Krauser-Raviart or weak boundary conditions. Okay, so how does it perform in practice? Okay, this is the same kind of drawing of the H1 error with respect to alpha. We've seen this top red curve, we've seen this orange curve, we've seen this purple curve. This pink curve here is if I do bubbles, but I define everybody with affine boundary condition, okay, failure again. And this green curve here is if I use Krauser-Raviart boundary condition, but no bubble, failure again, okay. But now if I use both, which is bubbles, and all of the basis functions defined with Krauser-Raviart boundary conditions, this is the result that we obtain, which is very neat. and very comparable to our best method that we used to have a few years ago, which was this purple. All right. So with this, we were happy. It performs nicely, and in the 1D setting, where Krauser-Ravier boundary condition and affine boundary condition just boil down to the same stuff, we may make a numerical analysis of the approach and understand why it performs nicely. Okay, but it's very much, for the moment, it's very much related to the 1D case.
The bubbles, I mean, the multiscale functions are not conforming.
Yep.
Did you have to accommodate for that in any way?
No,
okay.
Not at all. We keep, in contrast to discontinuous Galerkin approaches, for instance, we keep the, so of course, we keep the original variational formulation and bilinear form. We write it as a sum over each element as a broken, of course, but there is no penalization, if you wish, as there would be in the discontinuous Galerkin setting.
And you got good stability and convergence?
Yeah. We didn't go to fully discontinuous Galerkin stuff, because then you had to introduce this extra term to stabilize, which means extra parameters that people know very well how to choose in a single scale framework. And then, okay, that would be yet another parameter to fix. Okay, so a few words about, this is a question that Roland asked me a few months ago. So here is a short answer. It's really not a definitive answer, but still it goes in the direction. When you do a numerical analysis of the approach, you are going to estimate the error on the complete domain. You are not going to provide an estimate of the error in some part of the domain. Okay? So it means also that if you do the numerical analysis of P1 SUPG, you may do that, but the error bound is actually quite large, because anyway you are doing a big error in the boundary layer. Okay, and so why P1 SUPG is good, because this is what you see, there is no oscillations inside the domain, and to show this by a theoretical analysis is extremely technical. This has been done, but this is very technical. Okay. So a numerical analysis will provide you an error on the complete domain. So the only method for which I may hope to do an error analysis are the methods for which the error on the complete domain is good. Okay? Otherwise, the numerical analysis will say you are doing bad because you are doing bad in the boundary layer. Okay? So this is what pushed us to look at, now we have two methods that works nicely outside of the boundary layer. Let's see how they perform in the complete domain. Okay? So here's the picture, and this is now the error on the complete domain. For the two methods previously, that the MsFEM SUPG and that new method. Okay? For that one, we have no hope of being good in the boundary layer, because think again of a single scale framework. This is P1 SUPG, it does badly in the boundary layer. Okay? And indeed. Now, this is the method here for, this is our new method, which performs nicely. You have 20% of error in the complete domain. So if we are to do a numerical analysis, and this is not yet the case, but if we are to do one, this is only for that method, because this is only this method that provides an error which is small in the complete domain. Okay. All right, and this is where my answer stops. So it's really a preliminary thoughts. Okay. All right. To conclude on that part, and the second part will be much shorter, unsuccessful ideas that we tried, Petrov-Galerkin approaches, by testing with test functions computed with the adjoint operator. Okay? It's unsuccessful in the sense that it costs more, because you have to pre-compute again these test functions, and the improvement in terms of accuracy is not worth doing the job. Oversampling variants do not work nicely, because oversampling means that You put bad boundary condition far away from your system. If the system is diffusive, it will forget your boundary condition, and then this is not a big deal. If the system is convective, then the error that you put somewhere will propagate into the domain, and this is why oversampling, in our understanding, does not work so nicely as in the diffusive case. Okay? So we have two types of method, and then the criteria to choose which one you want to use depends very much on your situation. The MsFEM SUPG depends on the tau, and the tau may not be that easy to fit. Okay, and so this is one reason why you may prefer that first one. The reason why you may prefer the, this is the reason why this first method may not be very nice, because it has the tau. The reason why this method, the drawback of this method is that you insert the b in the basis functions, and so if you are in a setting where you have various b's, which happens often in that situation, then you would have to recompute the basis functions or do something on top of it, like model reduction maybe. Okay. So it's very much depend on your context. Yes, please.
Can I ask a question now before you get to the second part?
Sure.
So I don't fully agree or understand your comment about the oversampling.
Yes? Okay.
So in my opinion, if I just have convection and diffusion, and say the diffusion switches off somewhere, are you always in the setting where the diffusion coefficient is constant? Or?
No.
Okay, so if the diffusion coefficient is somewhere very small, then that inclusion will act almost like a zero boundary condition, so it will create a boundary layer just before that inclusion, or very large, one of the two. Create a boundary layer just in front of that thing. If that is right after your element, then oversampling will know of it, and non-oversampling will not know of it. So I don't see why.
Well, we look at a situation where in each of the, if you do oversampling, in each of the part of the oversampled domain, you will have somehow all the values of A epsilon. If you have now a specific structure, maybe you may use it. My sentence was...
But you have a specific A epsilon, no?
All these methods are built for handling non-periodic cases.
Yeah, but a specific A epsilon.
Yes.
A specific one.
Yes, yeah.
And that specific one will, in a specific element, may have some place where a boundary layer appears because it has a place where something blocks.
Well, what we tried was to look even in the 1D case. Okay, so you have 0 here, you have... Let me make a drawing since we have a board.
We can talk about it after.
Okay. We really tried hard, and and even in the 1D case, it did not. Maybe we missed something, but okay.
May I also ask?
Sure, please.
So this advection MsFEM, if you do it in one space dimension, does it reproduce the Ilin scheme such that the boundary layer is exactly in the bubbles?
Yes.
So this is why.
Yes, exactly. In the 1D case, and if the f is piecewise constant on the coarse element, for instance, then it is exactly.
It's Ilin scheme.
Yeah, definitely. But this is very much a miracle of the 1D case, because then the boundary is 1 point, and you can always fit 1 point, and then in the 2D case you have one edge to fit, and then you're lost.
So when you solve local convection diffusion problems, depending on the boundary conditions you use, you introduce boundary layers inside the elements that problem.
So we assume for the local problems we will pay the price and take a little h sufficiently small such that numerically it's not convection dominated at the local stage. Yeah, definitely. Anyhow, we have to pick a small h because of the A epsilon. Okay, so it's so it's time to move to the second part of the talk. Reaction-diffusion problems. Okay, so the beginning story is similar. We wanted to be far away from the diffusion case. So we looked at here this reaction and diffusion problems. You should note that there is a very strong coefficient in terms of the reaction term. And the reason is that this is a zero-order term, this is a second-order term, and with this scaling, in the corrector equation, both terms will appear. Okay? Otherwise, if this is a 1 over epsilon, or if this is a 1 here, then if this is a 1 here, you will just play with the average of sigma, and this is a kind of the standard case, okay? So this is why we picked that scaling. This is the mathematical reason. There is also a physical reason in the sense that this problem may be seen as a toy problem from the neutronics in the civil nuclear reactors, looking at the diffusion of the neutrons into the reactor. And for this application, by the scaling, this is the scaling which appears from the physics. Okay. We look at a eigenvalue problem. Okay, so we look at the lowest mode, lambda and u, satisfying this. And the other point I wanted to say is that, and this is what we discovered along the way, is that the u epsilon here is much, much more oscillatory for this equation than for the diffusion equation. I will tell you in a moment why, okay? And this is actually not that easy problem. Okay. It has been studied from the homogenization, theoretical homogenization viewpoint. There are many works by Grégoire Haller and co-workers, and let me recall them. So the idea is that we consider the first, so sigma and A here are periodic. We consider the first eigenvector of that problem, okay, in the periodic cell with periodic boundary condition. We normalize the psi. And since we look at the first eigenvector, and since we consider A to be elliptic, sigma to be positive, it happens that you have the Klein-Rootman theorem, which will tell you that the eigenvalue is simple. This is often the case for many PDEs. And the psi is simple, so, and it has a sign, and so we may pick psi to be positive. Okay? And now there is a magic computation, which is that you pick the solution u epsilon to that equation, and you consider v epsilon, which is u epsilon divided by psi. And you may do so because the psi has a sign. Okay? And then you do the math. It's not complicated. You do the math, you see which equation this v epsilon is going to solve, and you find this problem. Okay? So this problem is a purely diffusive. There is no reaction anymore. You have swallowed it into this change of unknown function. This is a purely diffusive eigenvalue problem. There is a v here, and this is the eigenvalue eta epsilon. And this is a generalized eigenvalue problem because here you have the psi squared popping out that was absent here, and that comes here. Okay? And the diffusion coefficient, which used to be A, now is A times psi squared. Okay? And this is really magic. Now, since you are on a purely diffusive eigenvalue problem, you can branch all the theory, and identifying the homogenized limit of v epsilon is not difficult. Okay, the A and the psi are periodic. Okay, so this is the whole story, and you treat this term as a standard diffusion term. So you introduce the corrector associated to psi squared times A. These are the Wi. You introduce the diffusion, the homogenized diffusion matrix A star associated to this corrector. So you are going to replace this diffusion coefficient by this diffusion coefficient A star here. And this term here does not create issues because you should remember that psi squared is equal to 1 in L2 norm. And this is a periodic function, so it weakly converges to its average. And the v epsilon strongly converge. Okay, so on the right hand side, it just boils down to simple thing. Okay, so the homogenized limit of v epsilon is v star. You have again strong convergence in L2, weak convergence in H1, and with the correctors, you may have a strong convergence in H1. Okay, all right. So this is state of the art of Grégoire Haller works 10 or 15 years ago. And this is a good moment to underline that if you read this equation, that means that u epsilon divided by psi is more or less v star, the leading order, which means that u epsilon is psi of x over epsilon times v star, which means that the solution itself oscillates strongly, and not only its gradient as in the diffusion problem. Okay? And if you look at the gradient of u epsilon, it is unbounded. There will be 1 over epsilon popping out of this term. Okay, so this is somehow a much more complicated equation than the diffusion equation for this reason, and we didn't know that at the beginning. Okay? All right, how do we do from a computational viewpoint? So let me proceed in two stages. First, we are going to do like a preliminary approach where we look at this, and it is preliminary in the sense that we assume to know psi. Okay. So we are in the periodic setting, we assume to know psi. So we do as in the theory, we change variable, we go there, this is a purely diffusive eigenvalue problem, and we branch on MsFEM, which is we design the basis functions associated to this diffusion coefficient, satisfying, for instance, a fine boundary condition here. We expect, and this is indeed the case, this V epsilon to be well approximated by the span of these basis functions as MsFEM lim in general. And since V epsilon is U divided by psi, U is V times psi, and then I'm going to approximate, the method consists in doing a Galerkin approximation of U into that span of chi, which were computed here, times the psi. Okay? This is the preliminary MsFEM approach in the sense that we assumed to know psi. Now, if we don't know psi, then we need to approximate it, and that was not easy at all. And the method that we found to reasonably work is this one. So we have these triangles. Now we are going to do oversampling, but in contrast to the regular oversampling, and I've never seen that, and I'm open to any suggestion from the literature, we are going to oversample this triangle by a square, and we tried, of course, to oversample it by a bigger triangle, but it didn't work. Okay? So we consider a big square here, S. We consider this eigenvalue problem on that big square with periodic boundary condition. This is the reason why we use the square here, to use periodic boundary condition. And then we consider the restriction of that guy computed on the blue rectangle on the triangle, and we do this triangle by triangle. Okay? So in the end, we build a function which is discontinuous on all of the edges of the triangle, and which is the restriction of this eigenmode. Okay, so this is our approximation of psi, and once we get it, we do the same game. Okay, so we use to build MsFEM basis function according to this problem. We replace the psi squared by psi squared. We use to approximate the u in the span of chi times psi. We now approximate it in the span of chi times t. Okay. Every time we use to see the psi, we replace it by phi. Okay. We tested it on two types of coefficients. The first one, which I call straight coefficients, which is this kind of drawing here, and the other one, which is a tilted coefficient. What we wanted to be careful with was that we have a very Cartesian mesh. Okay, it's made of squares that we divided into. Okay, it's a simplistic mesh. So of course here there may be some resonance between the mesh and the microstructure. Okay? Here it's tilted by an angle which is made on purpose irrational, so there is not, or at least we try to escape from this miracle. Okay? Here is how it goes. So forget about the black and the green curve and just look at the blue and the red. The blue one is the preliminary method. Okay, so h is fixed here, and epsilon goes to smaller value as we move to the right, which means that the problem is more and more oscillatory when we move to the right. And here it's more or less not scale separated because epsilon is more or less of the size of h. Okay. We see that the two methods perform nicely. On other examples, the red is a bit worse than the blue one, but not that much. Okay, and we do an error which varies between 30%, say, and 10%, which is not maybe as good as the 10% of oversampling MsFEM, but which is not that bad for this problem. It's the H1 error, okay, that we look here. If you look at the L2 error, this is 3%. If you look at the eigenvalue, this is less than 1% of error. This is for the straight coefficients. For the tilted ones, the colors are not the same, so don't be confused. This is the result with the P1 thing, which of course says that the P1 does not work. Okay, you're making 100% of error, so it is a truly multiscale problem. And this is the result with the actual MsFEM thing, again between 30% and 10%. Okay? And the same kind of errors if you look now into L2 or the eigenvalues, same ball. We also looked at various eigenmodes because we want to, we paid a huge price to build the basis functions, and when you are in a source problem, you may reuse it for different f. Okay? Now we are here in an eigenvalue problem, and so we may reuse the basis to compute the next eigenvectors. This is what we did here. H is fixed, epsilon varies here, so again you go to the right, it's multiscale. This blue curve here is the first eigenmode, and the other ones are the other eigenmodes. Okay? As always, for the Laplacian, if you look at higher modes, the accuracy will be worse and worse as you climb the eigenmodes, and this is why it goes worse and worse when you climb from blue to red. Okay? Now, if you decrease the mesh, it improves to 20%, 20%, and this size of the mesh is far from being enough for a P1 method to work. Okay? The P1 method on the first eigenmode and on the second eigenmode provides this error. Okay? So as soon as the problem is a bit multiscale here, you are doing a huge error with P1 in contrast to the MsFEM approach, which is then worse doing the game. Okay? All right, and these are for the other coefficients. Okay, so it's time to conclude on the scientific part. For that problem of reaction diffusion, we have a first batch of methods and numerical results. We already have some element in terms of theory, which is to say that if you look at the relative error between H1, between the preliminary, the solution of the preliminary method and the true solution, if you look at the relative error, which means that you rescale everything by this epsilon, because this guy is of the order of 1 over epsilon, you may bound the error by these quantities where you see the period and the mesh size, capital H, assuming little h is 0. Okay. The other points that we would like to go in terms of multi-query selling to make worse the computation of the basis functions is to go to a time-dependent selling. You may either do this in a spectral spirit using the different eigenmodes or by doing a time stepper. Okay? But anyway, we will compute the basis only once and reuse them for the various eigenmodes or for the various time steps. The red line, and I think that was a question also that was asked to Barbara, the red line between these two parts is that we discovered with the advection-diffusion problem, and this was confirmed by this problem, is that MsFEM is not simply taking, and this is probably the same for LOD, it's not just taking the original equation, LU is F, and introducing basis functions satisfying L phi is 0 or 1 locally with some boundary condition. Okay? It's something which is much more involved and much more difficult than this, and which requires some understanding of the problem. Okay? And this was the underlying thing of these two projects. Let me conclude by two things. The first thing is easy to say, we have money to hire postdocs. Okay? The second thing is a bit more difficult, I mean, it takes a bit longer to explain. We are going to organize with Alexei, and I talked to several of you already, an event in Chicago. This will be end of January or beginning of February in a few months. So this is 3 days of winter school and 1 week just after of a research workshop. Okay? So the winter school courses, it will be 3 courses, more or less 5 hours per courses, by Anthony Patera on reduced order modeling, by Sonia Fliss, that you may know, on homogenization, and Ulrike Maniuk on how to implement this in practice on a computer. We are very open to having young researcher, postdocs, or PhD students attending the winter school. They should apply for funding with Chicago. We are very flexible. The idea is that the people that come from for the first part attend the second part, if they may. Okay, and then they will be offered the possibility to present their own work. And if they just come for 3 days, they come for 3 days, and that's fine as well. Okay, so the two things were designed in a common fashion, but now it's up to you to what you want to attend, and you may see details on the Chicago website or on my webpage at the very bottom of it. Thank you very much.